Hi, I'm Philip, and in this video I want to show you a tool or a Python tool I created to easily convert a point cloud, so a PLY point cloud, to a Gaussian splat also in the PLY format. You may be a bit confused now what about it exactly this is. So my state is, or my original problem I had a lot of times, the 3D scanner, the lidar scanner, I've been a bit more into lidar scanner recently, creates a point cloud as like its default output format. In the point cloud, if you zoom in more and more, now let's turn down the point size a bit. Here you can see it. Each measurement is a point with X, Y, and Z coordinates and the RGB color value. This is quite nice, for example, for reverse engineering or direct measurement of the point. So I can now, for example, I can directly get the measurement tool and measure distances. But what I had as like a to-do on my list recently, so the to-do for me was to both allow like performant visualization in a browser, first in a browser, ideally on a device without no like performant GPU needed, and also for easy VR visualization. And the problem is a bit that both of these points, or all these points, don't work very well with point clouds, sadly. There are like some industry tools, for example, I think there's like for Faro, there is some software that can do it. Siemens NX also has some sort of VR plugin, but I wanted it to be natively supported. And to allow this, or to realize this, I stumbled upon Gaussian Splats. And these were a bit of like my savior in this solution, or in this situation. And the interesting thing is, for Gaussian Splats, we must compare them now to regular point clouds. And there you may see how I came to this approach, or to this workflow. So if we first look at a point cloud, we have like points, multiple points, a lot of points, and each point has like X, Y, Z coordinates, like this, X, Y, Z, and also RGB values. This is like a gross simplification, but these are the relevant parts that I will be focusing on here. So this applies to all of these points. And in comparison, Gaussian Splat, this is now in 2D, so not in 3D. It also is to some degree a point cloud, but around each point there is like a ovoid. So you can imagine a bit like a donut, or like a blood cell, or like a bacterium. Maybe a bacterium, if you have seen them, like these. It can be lengthy, it can be round, it can be like pancake shaped. It really depends on how it is defined. And so with a lot of these, and this allows to create a much nicer representation of the reality. And for each of these Gaussians, we still have the origin, basically. So that's the X by Z. Then we have the volume, and we have the color. The color itself is defined as a spherical harmonic. Spherical harmonics are a bit like basically what you can know, what can remember. Color changes depending on view, and this allows, for example, that reflections can be like quite nicely realized, and like changes, or subtle changes depending on the lighting. But what's the interesting thing now? The volume is, if I straight up want to like convert a convert a point cloud to a Gaussian splat, the volume can just be a sphere. And the color, this like very complex spherical harmonic, can basically be set to roughly represent the RGB value. So what in the end do we have now? We have an origin of each of the splats. That's the XYZ coordinates we already have. Then we have the sphere around each point. That's basically approximation to look nice. Nice. So this is like arbitrarily set to a value, e.g. like a value of -6. Then it looks nice. So to set this sphere size, I just tinker it around until it looked best. Right. And we have the color. And this one is roughly the RGB value. And the good thing is, the file format itself of this, like the file format, is in both cases .ply with a similar structure. And this is like these 2 points, or these 2 things, they let me to create PLY-TO-SPLAT. For context, I have IT background. I do mostly DevOps stuff, and a good portion of this tooling was wipe coded, as one would say, but it works. I mean, it works. It works cross-platform, and it uses for editing or for preparation the CloudCompare CLI. So if we have a look at the workflow, how this PLY-TO-SPLAT will work, is we have a point cloud in a .ply format. The relevant part is currently I only tested it for share 3D scanners. It may be that it also works for other scanners, but I cannot promise it. Most likely there will be some, probably there may be additional headers that need to be removed. But for the current time, I tested it with my Share C1 and S20, and it worked in both cases. Then what I'm doing, I have like my tooling envelope, I would call it. And within this tooling envelope, there are, as the first step, is the usage of the CloudCompare CLI. CloudCompare CLI. This one is used for multiple things. It subsamples, so it reduces the point size or the point cloud data or amount of points. Then it filters a bit, and it transforms. So for the transformation, it's relevant that normally Y becomes set, basically. This is like the first part, and the second part is Python script. Python script, and this is used simply to convert. It's now like this. This is used to convert the point cloud to the to Gauss. And afterwards, what you can do with all these, like with these adaptations or with the new data, it's free to you. For me or for myself, I quite like to use it in Supersplat, or import it in Supersplat. So import Supersplat. But this is like anything you want to do. With a splat. But now let's have a look at how this is looking in real life. So I have my point cloud here. This is just test 3D scan I did in one of the nearby living blocks in the city. And as you can see, it's a point cloud, of course, and I already exported it as a .ply file. Now we have a look at the GitHub project. Most important thing for you will be the README as a starting point, and there is exactly described what you need to do. Basically, the prerequisites you will have. You need to have Python installed. It can be either Windows or Mac OS. I tested in both platforms, so even Apple Silicon. It should also work on Linux, but I haven't tested it on Linux. Then you need to install the Python requirements in a virtual environment, so Python virtual environment, basically with these commands. And if you want to leverage the CloudCompare editing of the point cloud, you also need to have CloudCompare installed. I tested it on macOS and Windows with CloudCompare. I just used the latest CloudCompare version, and the script automatically finds the install direction or checks the most traditional install directions. For using it, I would say the default one to use, or the one I would advise you to use is to just use the prepare and splat scripts. These are wrappers that call the two Python scripts, so the CloudCompare prepare.py this one does the CloudCompare editing, and the PLY-TO-SPLAT py script that performs the actual transformation. And you just basically, you just call it. Also, for example, on Windows, it will be this command, and give it the input.ply and output.ply paths to the so the input.ply path to the actual input point cloud file, and the output.ply path to the file output splat you want to have. So I already exported the building block as a PLY file. So what I can do now is I will call prepare and splat. And I will first define the input file, so the point cloud.py, and the output will be called splat.py. And now I just can start it. You may get this Python incompatibility statement of CloudCompare. You can just ignore it with OK, it isn't needed. Now you can see that CloudCompare was called over the CNI with different options. For example, I will perform a global shift to center the point cloud. Then I will apply a transformation matrix to switch the Y and Z axis. This is important because, for example, Supersplats treats the coordinate system a bit differently. Then I perform subsampling with a 0.75 centimeter resolution. This one was like a bit of a sweet spot value for mine, I discovered. Sorry, let's go back to the calling. And then I export it as a temporary point cloud. You can see here the CloudCompare finished running. And then in the next step, here it is reading the lidar data from the temp file and performing the transformation itself. So what I can do now is I can open Chrome and load the file. So I have to check that I'm not showing anything that I don't want to show from my PC. So here we go. Here's the Git repo. All right. So like this. And I can now open the splat.py file. We are currently in the Supersplat editor. So this already only works with PLY files. So, with Gaussian Splats. So keep this in mind. And so as you can see, it loaded. And we have a Gaussian Splat. I can directly freely move it or transform it in the software. So for myself, I achieved my goal. So from here on, you can, for example, export it as a SOC file, upload it to Supersplat and view it in VR. So for me, this was really for the point of just getting a very easy workflow from lidar scan data to something I can share with people online or over the browser. I am aware that there is like proper Gaussian splat training. Don't worry, I already also do it, but this is just vastly faster. And I don't need to perform like the full training. I don't need to throw my very capable GPU at it all the time and let it run multiple hours to train a nice model. So this is good enough. You can also view it in a browser. So I'm very happy with the result. I hope this might help you. It's to some degree. Maybe you have the similar use case. I've seen that someone maybe already did something similar, because I found a similar point cloud to Splat on Supersplat when looking around if there already is such a tool, but I didn't find the tool itself. So I just decided to create it myself. So have a nice day. Hope you enjoyed it, and be back when I release more, hopefully interesting stuff.